Hello and good afternoon or good morning, wherever you are in the world. Thank you for joining us for this webinar, Focus on Geothermal Energy for the Weekend. My name is Alexander Richter. I'm the editor of Think Geoenergy, and I'm very pleased today to have here with us as a presenter, Professor John McLennan from the University of Utah, who will be presenting on the Utah Forge project, so the Frontier Observatory for Research in Geothermal Energy, give us a status update and looking ahead of the project. John McLennan is the lead reservoir management and the co-principal investigator on the project and is leading the resource management activities of the project. He's the associate professor in the Department of Chemical Engineering at the University of Utah and an adjunct professor in the Department of Civil and Environmental Engineering. And interesting enough, also a strong industrial background in the petroleum service technology companies in the United States. And with that, over to you, John. Thank you again for joining us for this webinar, and very much looking forward to hear your presentation.
Thank you all, and good morning, good afternoon. Energy for the weekend. Well, it's a long weekend in the United States here. But I will keep the talk precise regardless. And as Alex mentioned, I will be talking about EGS at the Utah Forge site. And this is a Department of Energy site where enhanced geothermal systems are being tested out and developed in advance of commercialization, to promote commercialization. And so I'm presuming that most people in the audience are familiar with what a classical EGS system is. It's a conventional hydrothermal system minus the convective fractures, minus the hot fluids. And the obligation of an EGS is to add to the heat the fractures through hydraulic fracturing in jurisdictions that allow that, and the fluid that can circulate. And so the EGS pilot at the Forge site in central Utah entails the schematic that I'll show here. So the first thing that's involved in producing one of these sites is to have some sort of an injection well. And at Forge, we have indeed drilled this injection well. After the injection well is drilled, a set of hydraulic fractures are created that will ultimately join with a production well. And we are at the point now at the Forge site where we've drilled the injection well. We've done a small set of hydraulic fractures at the toe of this injection well. And subsequently this fall or early next winter, early next year, we will drill the injection well to establish the basics of a heat exchange system. In a commercial setting, there would be fractures all along the length of the two well bores to provide large surface area for heat exchange to occur as fluid moves from one well to another through the fracture system. So conceptually, in a commercial setting, injected cold water would circulate through the fractures that are created. And I'm using hydraulic fracturing. There's possibilities of thermal fracturing or acid fracturing in certain settings. Once that hot fluid gets to the surface, it's conventional conversion to power in a geothermal setting. So at the Utah Forge site, we've currently drilled 6 wells. Now, most of those wells are monitoring wells, and you can imagine monitoring wells are required because this is a pilot. This is a scientific pilot that is designed to test out and extend these technologies. But in addition to these monitoring wells, one injection well drilled at a 65-degree angle to the vertical has been completed. And we're going to call that well 16A. And that well has been completed. On the aerial view to the left, you can see the vertical projection of that well. And you can see surrounding wells where geophones are in place and other monitoring operations will be ongoing. Now, to give you a perspective of the temperature, it's high enthalpy, but not extraordinarily high. The bottom hole temperature at the toe of this well is about 230 30 degrees C. But regardless, as we know within the geothermal community, that temperatures of that magnitude are the blessing and the challenge of the geothermal system. And there's the challenge because they preclude the use of many conventional monitoring stimulation technologies, isolation devices, packers, and things like this because of temperature limitations. And indeed, if you look at availability of equipment, apologies for the temperatures in Fahrenheit, but if you look for the availability of equipment, there is some logging equipment, maybe some density logs and some multi-finger calipers and other devices that go to 500 Fahrenheit. But in most cases, there's a restriction on logging tools at 300 to 350 degrees Fahrenheit. And obviously, as we all know, that has consequences in terms of reservoir characterization. Similarly, in terms of drilling and steering, MWD tools commonly have even a 275 degree Fahrenheit limitation. So temperature is the first issue that we all have to deal with in the geothermal community. Secondly, particularly in these EGS systems, is that we're dealing with the quandary of what is the role of natural fractures. And indeed, we often find that if we look at current understanding within the oil industry, and let's look at the right-hand panel, we see microseismic signatures that suggest hydraulic fractures have occurred in a relatively planar fashion. And as we know, in pretty much any reservoir that we deal with, there will be some degree of natural fracturing. But evidently, in these particular situations, the stress field or the characteristics of the injection program or whatever have led to relatively planar fractures. Now, one asks yourself, then in this geothermal setting at Forge, if we move to the photograph at the left, which is actually the Forge reservoir, what are the implications of these natural fractures? Now, certainly these fractures are exaggerated in this outcrop because of erosion and de-stressing. But there are many, many fractures that are mapped in situ, and one of the challenges is understanding the role of those fractures. A second role of this program at Forge, beyond understanding the role of fractures, overcoming some of the temperature limitations, is dealing with some of the geomechanical quandaries that we often face in terms of the ability to have these hydraulic fractures intersect two wells. And this is not a new concept. This was pioneered at the Fenton Hill project in Jemez Caldera in New Mexico in the late 70s and early 1980s. And here is an example where a large hydraulic fracture was pumped in well EE2, attempting to intersect well EE3. And these wells, as you can see, are subvertical. But unfortunately, if we look at the microseismic signatures back, and this is one of the earliest applications of microseismicity as a monitoring tool, we can see the production well EE3, we can see the injection well EE2, and we can see that most of the seismic activity forecasts fracture growth that did not lead to an intersection. And in fact, that was a complication at this site, that the intersection was weak. So nevertheless, we have updated drilling technology that allows us to steer these wells. And this is the reason why you saw in the earlier diagram, we're drilling one well first, fracturing at the toe of that well, monitoring microseismicity, and then drilling the second well into the microseismic cloud with the anticipation that we will be able to establish some sort of connection. Now, so we're looking at operationally, we're looking at directionally drilling these wells in an appropriate direction. We're also looking at developing packers that will allow isolation along the length of this injection well so that we can create multiple fractures. And one of the things that has been encountered here has been the difficulties in having packers function successfully. And so that remains a challenge. And actually, this Forge program is sponsoring research through the Department of Energy to try and address some of those issues. Other problems that we are trying to address at this particular site relate to drilling. And this is one of the, there are many aspects of the drilling with the application of PDC bits that has dramatically changed the rate of penetration and the time on bottom in these wells. I don't have time to talk about this, but I just have to show one particular interesting aspect of drilling in this granitic reservoir and steering. And what you can see from these reconstructions based on a UBI is that the wellbore is very rugose in these granitic rocks, and that no amount of reaming seems to work out this rugosity. Much of it is related to going from sliding to rotating as you're directionally drilling. But this roughness is interesting, and it potentially produces some future challenges in terms of pinching off of cables and stress concentration points on cemented casing. Okay, so that's sort of a very quick background. We have a situation where we've drilled the first sub-horizontal well. And we have just finished creating some hydraulic fractures at the toe of that well, and we're trying to comprehend the issues of the temperature, the issues of the natural fractures, and some of the operational considerations. And those all come into play in terms of the hydraulic fracturing stimulation that was just carried out in April of this year. Now, to be honest, that stimulation is not substantially different than the large stimulation I described at Fenton Hill, done in late 1983. That stimulation used slick water. Slick water is strictly water with friction reducer added. As you can imagine, you're pumping at a high injection rate in this particular situation at 50 barrels per minute and about just under 6 million gallons of fluid. So a lot of fluid, a high injection rate, and a little bit of solid particulate matter added for diversion. Now, candidly, the stimulation treatments that we adopted at Forge were not significantly different. They were done in this particular well, and you can see the cross section of this well here. And those treatments were done right at the very toe of this well. And the first treatment, in fact, was done in a 200-foot open hole section of this well. So below a measured depth of just under 11,000 feet. And like the Fenton Hill treatment, this was done with slick water at up to 50 barrels per minute. And there was an organic tracer that was added to this particular stage. Subsequently, the second stage, we flowed back the first stage, moved up the hole into a cased section. We isolated this case section, and we isolated it with bridge plugs, and I'll show you those in a minute. And the bridge plugs overcame some of the temperature limitations. But once again, we pumped a slick water treatment with an organic tracer. After flowing back that, we moved up the hole and isolated and perforated again, and pumped a cross-linked fluid, a cross-linked CMHPG fluid with an organic tracer. So in particular, trying to overcome and dealing with, what I talked about earlier, the temperature limitations, we searched around and we were able to find a company that was able to provide devices that qualified at the temperatures and pressures required. And this turned out to be Interwell, a company out of Norway, also with US operations. And their bridge plugs worked extremely well. And the only drawback was that the setting tool for these bridge plugs could not tolerate the temperatures if it was a wireline set. So that meant that we had to have a rig and run these on pipe. But nevertheless, for this particular experiment, this was an adequate solution, and these worked extremely well. The second thing that we addressed is that we wanted to qualify modeling that had been done. So Idaho National Laboratory, Itasca Corporation, and Golder had all contributed to modeling, wherein they had looked at various scenarios of natural fractures being present. Discrete fracture network modeling was used to represent this. And I'm showing a range of scenarios that we were trying to quantify by these hydraulic fractures. Whether you have permeable frictional DFN network and a very diffuse propagation of fluid through a broad area, or whether the DFNs are less permeable and have some strength and lead to a fracture morphology, something like this, or in the extreme case, as we might even imagine from what we saw of that example in Texas, where there's basically ignoring the DFNs. And so we were able to, and we're working at least, to back analyze our microseismicity and understand this. So stimulation carried out in April of this year, 3 fracturing stages at the toe of this well. This is a 60-degree angle to the vertical, those 3 stages that I described, and monitoring wells with geophones to depth and relatively shallow DAS cables in this well and in this particular and in this well, 56, 32, and 78, 32. So prior to the first stage, we also pumped a low rate injection test, trying to assess if shear stimulation had any impact. We had already tried something like this immediately after we had drilled the well. This would be in the open hole section of the well, pumping at a rate of a very low rate, 0.36 barrels a minute, less than 0.06 cubes a minute, and pumped not a large treatment. But what we tended to see is that this fracture just opened up, just like a door, and there was little microseismic activity, as I understand it, and so there was not a significant amount of evidence that would suggest that shear stimulation was going to be effective. We followed this immediately with a higher rate injection, as I mentioned, and this is in the open hole section of the well, at about just under 8 cubic meters per minute of slick water, and just under 700 cubic meters were pumped. And as you can see, the pressure record is in red, the rate record is in yellow, and up to 50 barrels per minute. We didn't quite know what was happening, so we just walked up the rate gradually and then kept it at 50 barrels per minute, and then did a step down afterwards. Successful treatment. The interesting thing about the pressure in this, it's a 200-foot open hole section, is that as you can see, it's very different than the pressure profile in a cased and perforated section of this well that we'll see shortly. So we completed that first section, and we flowed the well. We actually flowed the well back. We floated back because we were uncertain of whether there were going to be any quote-unquote poroelastic effects, poroelasticity in a fractured medium, mind you. We floated back, and then we ran into the hole with the bridge plug. And you can see the elastomeric seal of this bridge plug, the bridge plug in the center photograph running into the hole. The bridge plug was successfully set and tested to 7,000 PSI, and then ran in the hole with a perforating gun. 20-foot gun, 6 shots per foot, 21-gram charges, as I recall. And the reason that we ran such a long gun is that we wanted to ensure that we would encounter some sort of natural weakness along the way that would help with the initiation or initial propagation of the hydraulic fracture. So we've carried out the first stage. We've set a bridge plug to isolate the first stage. We perforated above that bridge plug to provide access to the formation again, and then Liberty Oilfield Services pumped the second stage. Once again, a slick water, so water with friction reducer, about 440 cubic meters of fluid pumped at 5.5 cubic meters per minute. A lower rate because there will be perforation friction here. And the interesting thing, and there were 2 intentional shutdowns partway through this treatment to monitor, see if there's any change in seismicity, and to look at water hammer effects. And you can see that there's a very, very different morphology of the pressure. And we have not had time to do the modeling to fit this, but this is a classical pseudo-radial pressure phenomenon for a single fracture. And indications are that we have a relatively simple fracture system. We flowed the well back after we had shut in this particular well. Once again, we flowed the well back. We went back in the hole and set a bridge plug above those perforations, perforated above the bridge plug, and went in with the third fracturing stage. The third fracturing stage was a cross-linked fluid pumped at up to 35 barrels per minute. And once again, you can see characteristic radial fracture behavior, and preliminary microseismic events suggest a feature that is relatively radial in characteristics and relatively constrained laterally along the length of the well. Much more analysis to be carried out, and I need to really acknowledge the strong work and the great interaction that we had with Geoenergy Suisse on this particular project. So we've done this frac. The next stage will be to drill a well to intersect that fracture, and once we intersect, we're going to evaluate four things. We're going to evaluate and, if necessarily, mitigate the degree of conductivity. We're going to ultimately have additional experiments where we assess the role and how to change the conductivity of the fractures, proppant, for example. We will evaluate conformance, which is going to be a particularly important issue. Conformance being equality of flow within each one of the fracture systems. And then ultimately, we will look at thermal depletion and how much electricity could theoretically be generated from this site. So that's a very brief overview. I'd like to thank the Department of Energy, and I'd like to thank all of our partners on this frac job. There's just too many to mention, but it was I think an outstanding success. All this information will be public, and we hope it will be useful and fodder for a lot of analysis and insights.
Well, thank you, John. Utterly interesting, and I guess there's a really a few questions and thoughts here. But I see that there are already quite a few questions in the Q&A, and if you have any additional questions, please use the question opportunity that you have in the system here, and I will try to take through as many questions as possible here. But maybe first of all, John, I mean the Utah project was a big milestone, I guess, for the geothermal industry in the US or internationally, I have to say. But it was chosen from several projects. So in the context of basically then being the final project, now being under this full funding of DOE, is there still relationships between the other projects, and what do you think that project of Utah will mean for the other potential sites in the United States?
Actually, there will be a revitalization of some of these other projects, I can imagine, because I think that the federal government in the United States is going to allocate additional funding at some time in the future to development of these multiple other sites. So I think that what we have found here, particularly in terms of drilling and the success of the stimulation, will lead to accelerated development of those sites in other places. And just to provide a little more background, the Department of Energy initially allocated 5 sites within the United States for paper studies in terms of something that meets the criteria for an EGS site, and those criteria were temperature in excess of what was it, 175 C, and maybe up to 225 C. Hot enough that it's going to be challenging, but not hot enough that it's going to be an impediment. Temperature, a granitic, a crystalline igneous reservoir, limited environmental considerations, minimum seismic potential, and that's one real attribute of this area, and favorable environmental considerations. But I think that there will be future funding, and some of that funding and or the learnings from this site will quote unquote stimulate activity at those other areas.
Well, thank you so much. So let's then jump into the question, like trying to group them, and we'll see if we get through at least most of them, but maybe just starting with the first one here. What are the minimum and maximum distances of injection and production wells and the limits of changes in the energy source with respect to the fractures and seismic activity?
Okay.
And type and permeability of the reservoir, so quite a long question.
I'll start, and if I miss part of it, please remind me.
Yeah.
So our sense is that we will drill the second well vertically offset this, the production well vertically offset this well by about 100 meters above. And the basis of that was our sense of from modeling and other insights of what the vertical extent of a modest-sized hydraulic fracture was going to be. And so we initially inferred that direction so that we would be relatively certain of connecting with the hydraulic fractures that were created at the toe, because that's the number one criteria of this project. We have to establish that we can connect. You know, in the oil field, they try and avoid it. They call them frac hits. Here, we want to encourage the interaction. So 100 meters we felt that we can do, and it looks like from the preliminary seismic evaluations on stage 3, for example, that's not a bad guess. What we don't know at this time is whether or not that distance is large enough to provide, to be commercial. And so that will come as we do circulation testing after the second well is drilled and the connectivity is established. So 100 meters.
Okay, I think I think it's the best we can do. And next question here, and if you could comment if you're using proppant in the fracs.
Yeah. In this particular case, we did not use conventional proppant, and that's not quite true. In the third stage, we pumped what's called microproppant, and microproppant is finer than 300 mesh, maybe even 400 mesh. I can't remember the specs. And the reason for the microproppant is just to provide another indicator in addition to tracer for when we drill through a fracture with the second well. That we plan on mapping, because we ran 3 separate tracers, one in each stage. We'll drill in and we'll monitor when we hit the tracers. And then potentially in the third stage, we might see the microproppant. We really don't know. It may or may not be visible. However, the question is completely relevant. It's a very important question. You know, the #1 task is connectivity. We want to establish connectivity. We did not want to screen out. That's why we did not pump proppant in this stage. However, in the future, one has to establish fractures that are adequately conductive, and potentially you can use the proppant and other additives as diverter to either simplify or complicate fracture networks moving between the 2 wells. And so I think at some time proppant will be required. The complexities with proppant obviously rely on long-term integrity of that proppant at temperature and in an aqueous environment. Silica is likely not a candidate. In the lab previously on the Raft River project and elsewhere, we've had good laboratory success with bauxite. Some other people have had less success with bauxite. So proppant is likely going to be required. If I might just talk a little bit more on the proppant, because it's an important topic. One needs to look at placement of the proppant. In the oil and gas industry, they increase the concentration of the proppant as the frac job goes on, so that they have a nice wide propped fracture at where they're injecting the fluid. What we need in this particular case is we need the conductivity at the tip of the fracture where it intersects the production well. So there are some intellectual challenges in terms of developing a proppant schedule that's going to adequately prop the well.
Okay, then, well, like I said, I'm just trying to kind of go through this here, but they're all over the question, so I'm just going here one by one. The question here, if the circulated water inventory is constant, or if there's water added from underground sources that are lost to the underground over time, and what's the overall balance, do you think?
Yeah. Once again, we will carry out circulation tests to determine what that overall balance is. This is nominally a closed loop where you're injecting water, you're producing water, you're running it through a binary plant, you're recovering that. You're ideally recovering and re-injecting that water into the cool loop. There is ultimately going to be some loss into the formation, but we don't think it's going to be very much. And the reason for this is that with all of our drilling, for example, we've had very, very low fluid loss during the drilling. And during the hydraulic fracturing, the shut-ins have taken a very long time, indicating that there's relatively low permeability. That being said, we really won't know the answer to that question until we carry out circulation tests after the second well is drilled and the connection is established. And that's a very important question, looking at the overall water balance. This is a desert area. We do have water supply, and I forgot to mention, one of the reasons that this area was selected also was that the water supply is not potable. We're not competing with agriculture. We do have rights to water, but we just assume have it as much of a closed system as possible.
Okay. The next question here, are you planning or have you taken cores along the main horizon in the producer well to evaluate the connectivity of the wells?
We will. We have taken core in a number of two vertical wells, and in the injection well, we took core in the vertical section, and we actually took about 50 feet of core right at the toe of this of the injection well. In the production well, we're just putting together the well program for drilling that well, and so that well will be drilled, late fall, early spring. And currently, we have written into the program that we'll allocate 500 feet at the toe of this well for coring as much of that zone as we possibly can to look for intersections with the fractures. So actually a very, very, very good question, because understanding the connection with these fractures is extremely important, and we'll core as much of that 500 feet as we can within the economics, recognizing well, at least our experience in coring in these inclined holes has been a great deal of difficulty with core jamming, and multiple runs are required. But I think we're going to set our aspirations high, and we're going to try and core as much of that 500 feet at the toe as we possibly can.
Maybe give me some questions here regarding a certain information. What I would like to kind of encourage people is to kind of check out the Utah Forge website. The link should be easy to be found. There's a lot of information on the website, I guess, from the current activities, and some details. There's also been a lot of scientific papers being published during the World Geothermal Congress, for example, or the GRC events over the years. So check those out to kind of also, I guess, learn more about the project and the research. But let's continue with the questions here. Maybe here, kind of like a very practical or simple question. How much is the expectation for the production of the wells then in the end, if you were to put this into capacity of power generation?
I mean, that is a tough question. I mean, I'm thinking that let's look at this overall. Is that, suppose one had, in this particular case, we've got a relatively short lateral, and suppose you have 30 fractures, 30 stages along the length of that well, and each stage is taking I don't know, a few hundred gallons per minute, ultimately producing maybe 5 to 6 megawatts in this particular well. But I personally have not done those calculations. My colleagues at INL have done circulation calculations, and if somebody would like additional information on that question, I can definitely put them in touch with Rob Podgorny at Idaho, who probably has a better feel for the circulation.
Okay, perfect. Like I said, these are these kinds of like on-the-spot questions that are always hard to answer. But thanks for trying. Here, another question. You have drilled a relatively high-angle well, and you also talked about rugosity, but evidently you have been able to run image logs. So the question is, did you have any problems running wireline tools with TDE?
Yeah, that's a great question. The 65 degree, originally I was advocating for drilling the well at 90 degrees, but I was talked off the ledge for a couple of reasons, just in terms of safe easier operations in an initial well, and secondly, 65 degrees is about the limit for moving wireline tools into the well by gravity. Sometimes even 60 degrees you can get away with it. We found that 65 degrees we could not get in by gravity alone. We had better luck, and actually good luck, running it in on taxis. We used Schlumberger for this particular well, but other people have taxis. Schlumberger's service is called Petromac, and it's like a three-dimensional skateboard that has multiple wheels on it and rotates in multiple directions, but carrying a logging tool down. We were able to get logging tools down on this device. However, most of our logging, including our FMI logging, was done using through-bed technology. And the through-bed technology is basically where you have a bit run into the hole on the end of drill pipe or whatever. That bit has a hole in it. After that bit gets to bottom, and you're circulating chilled fluid the whole time that this goes down, because you've got an open face bit with a hole in it. Pump down your logging string, and that logging string actually goes through the bit and latches into the bit. There's a wet connect at this point, and once it's established that you're getting signals, you release that wet connect, and you come out of the hole with your wet connect, and then you come out of the hole with your tubing with the logs on the end, and you log on memory. And this worked extremely well. This was a very, very efficient logging methodology. But that's a very insightful question. That 65 degrees is just about the limit of the angle for moving logging tools into the hole with assist. Tractors were too expensive and couldn't tolerate the temperatures.
Okay, I'm trying to keep this somewhat sorted, but it's probably hopeless. So here another question regarding the microseismic earthquakes induced by pumping. Have these happened during the pumping or after the pump operation?
Yes. We are still processing that data, and Geoenergy Suisse and Schlumberger are working with the University of Utah to do that. There were signals that were recorded during pumping, and as is commonly the case, there were a substantial number of signals that were occurred immediately after the pumping and during shut-in, and some sporadic signals that continue to occur for some period of time. The largest signal that was recorded, I believe, was 0.2 M. But pretty much, as would be expected, that the shear events were recorded during and after pumping, and as we anticipated, there were no anomalously large events.
Okay, so next question, the estimate of the frac half length that was achieved.
We haven't done the history matching for the models, but I suppose if one goes back and looks at this, where I would guess a frac length is it's a pseudo radial fracture, maybe 150 meters in dimensions, maybe slightly higher in the vertical direction. almost like, possibly like an inverted pear, relatively planar. But I think it in terms of height growth, which we're most interested in, it looks like it's very favorable for intersection by the second well.
Okay, here then the next one. How much pore space have you created in between wells based on the tracer tests?
Could you repeat the question? I'm not sure that I completely understand.
How much pore space you have created in between wells based on the tracer test?
Well, all we've done with the tracers at the present time is we've injected the tracers in each stage, and we flowed back and monitored the tracers. So I think that we have really no quantifiable interpretation from the tracer at the present time. We'll be able to do more interpretation of the tracer once we drill through the tracers with the second well, and possibly bullhead the tracers a little farther through. So I don't think we know the answer to that question yet.
Okay, then next question is, have you considered to use CO2 as the fluid to extract heat in the future?
Yes, there remains a lot of interest in terms of using CO2 and in terms of Brayton cycle technology, for example, at the surface. At the present time, you know, we've been working at EGS for 50 years. You know, as you can see in the figure in the bottom left, we've had some fantastic scientific successes, but probably not probably not huge commercial success at the present time. Certainly not in the United States. And we need to establish some basic feasibility scenarios before we move to CO2. And as I indicated previously, our goals are, first of all, to establish connectivity. Secondly, to ensure that we have conductive fractures. And third, to establish that we have conformance, that we have methodologies for equality of flow through each fracture stage. And then at that point, we do an evaluation of the thermal depletion. And that's when you start with your circulation and assessing thermal depletion. That's when you start to look at other working fluids. And so this will come, but we're trying to be very, very prescriptive in terms of how we prove out this technology.
Okay, so then here again, this a long question, but let's see if I can get this through here. The rugosity of the well. Firstly, do you get a sense of how normal that is for similar wells, either in granites or other rocks? And secondly, do you understand what's controlling that? Is the in-situ fractures, granite variability, or something to do with the drill string?
Okay. Yeah. My sense here is that this is seen less often in softer sedimentary rocks in the oil and gas industry. We work very closely with two senior drilling consultants at Texas A&M University. This would be Fred Dupriest and Sam Neunert, and these people have a lot of industrial experience, and they were relatively surprised to see this happening. And you know, their previous experience had been, you know, in oil field scenarios, and so we sense that the high strength, the modulus, the abrasiveness of the granite is contributing. This you know, whether natural fractures play a role or not, I don't think we can completely say, but my sense is probably less so than the mechanics of the drill string, the stiffness and the vibrations of the borehole assembly, and high frequency torsional oscillations that are encountered in drilling this particular rock. And so in future stages, there remains a fair bit of research that will go on in terms of the drilling. And that research will, some of that research will be there'll be three things that research will be looking at. They'll be looking at reducing this rugosity, and we think it's partially related to the granite, but largely related to the characteristics of the bits that are being used. And some modifications could include increasing the length of the shank on the bit. And that being said, we just made fantastic improvements in bit design here. Switching from roller cone bits to PDC bits reduced our drilling time by 50%. It's made a huge difference in drilling these wells, and I strongly advocate this. And as we went on, we made further improvements. I'm not sure we've improved the rugosity yet. And what will happen with improving that rugosity is changing the bit design, changing the stabilizer considerations on the BHA, and ultimately, if we can do it, and we're going to try it, is running rotary steerable devices where there's steering on the fly. A lot of these changes happened. Many of these ledges seem to correlate with going from sliding to rotating, and so I think there's a lot that can be improved further in terms of drilling procedures to reduce the rugosity.
One of the questions that I thought was interesting here as well is the mitigation of the potential short circuits between the injector and the producer. Can you kind of talk a little bit about that?
Well, the interesting questions are the hard ones to answer. Yes. First of all, we want to diagnose how much of that we are actually going to see, and one of the reasons that we ran individual tracers and flowed back between each stage was so we can see if there's interaction between the fractures during the flowback. And we did not see that. We saw that the tracers were completely independent. So our sense is, I said earlier that we didn't have quantitative information on the tracers, but we have qualitative information. We did not see significant contamination of tracer flowing back from stage 2 that included stage 1, or tracer flowing back from stage 3 that includes stage 2 and stage 1. And so the tracers tend to suggest that these fractures are distinct and isolated. And they were quite a distance apart. They were a few hundred feet apart, a couple hundred feet apart. So that's not too surprising. But the question is a particularly relevant one. Suppose that interaction does occur and you're seeing it occur. How can you try and resolve that? And the standard considerations. The first thing you do is you put the stages farther apart. Well, of course, that's undesirable because it minimizes the number of fractures that you're going to be able to put into the formation, reduces the surface area, and reduces your potential thermal output. So if you're stuck with having fractures relatively close together, and you want to minimize the short circuiting and the interaction, what can you do? Well, the possibilities are, when you're actually treating, does the fracturing fluid that you use make a difference? This is why we tried to run a cross-linked fluid in the third stage to see whether a viscosified fluid would make any difference. Now, candidly, the viscosified fluids that currently exist and are at least readily available do not tolerate these temperatures well, even these modest high temperatures. We did get higher viscosity with that cross-linked fluid, and one of the things we want to see is whether or not viscosity itself can be a controlling factor by precluding flow into natural fractures. Then it goes back to the question that was posed earlier on proppant. Can proppant or some sort of particulate material or whatever serve as a diverting element to simplify, or if necessary, change the trajectory of fractures as you're going, and maybe even as a refracking treatment for mitigation. So very relevant question. Our evidence to date in this particular reservoir is that we feel pretty good that we're not having interaction between these fractures and short circuiting. But it's something that's going to occur, and through the course of this project, by injection of different fluids and different proppants, and the R&D that's going on, we hope to come up with some at least suggestions in terms of a workflow that people can try.
So John, like, there's a ton more of questions, but it's a question if you're ready to answer a few more, or
Oh, of course, of course.
of course. Okay, well then we'll continue here. So yeah, one of the practical question here is, like, if you were able to share the presentation with the audience afterwards.
Of course.
Okay, then I would kind of say that we would publish this on Think Geology as a news piece, and maybe the Utah Forge could also share this on the website. Okay, a lot of questions here, also some particular technical questions on the equipment, but maybe in that context, John, maybe a little bit discussion. You mentioned choosing a specific company for the drill bits and the fracturing. How has that process been of choosing the technology partners, and how, let's say, how international is that concept here, and the interest of these companies to engage with Utah Forge on studying and learning from this project?
Well, you know, there are some practical restrictions in terms of who the suppliers turn out to be. This is a federally funded project, and the prime is a state university. So by virtue of that, there are purchasing regulations, and everything has to go out to bid. And so the bidding for these services turns out to be, maybe a large portion based on technical capabilities, and a smaller portion of the evaluation based on costing. And so indeed it has, to a certain extent, been difficult to find organizations that, one, can provide equipment that meet the specifications. I think there's lots of people that are interested, but you know, finding somebody that can have a tool that can tolerate 8,000 psi at 240 degrees C has limited the field, particularly when you know, you require some sort of certification or proof that, at least in a laboratory autoclave environment, that's going to happen. So we are always interested in developing these partnerships, and we encourage technical interactions, and we'd like to make these wells open for people to use, but it's a situation of do no harm, that you know, we have an agenda, and we can't jeopardize the wells, but please communicate with us so that we can see if there's a potential for evaluating technologies at some time in the future. We've been very lucky with the partners that we had. As I mentioned, the companies that eventually participated in this frac work were sophisticated technology companies, and they were very, very vested in terms of successful geothermal technology.
Okay, here one question. PDC drill bits performed very good at the projects. Do you think they will become the future to drill in hot rock?
I would have to think so. I mean, you know, in the oil field, we saw largely a progressive displacement of roller cone technologies by PDC technologies, and certainly, you know, I can't say what's going to happen in other geothermal lithologies, but certainly in these granitic lithologies that we're drilling in here, there is absolutely no question that PDC bits, despite their increased cost, reduce drilling time substantially. As we went through from PDC bits to 3 wells, or excuse me, as we went from roller cone bits through 3 wells drilled with PDC bits. On our first roller cone well, we drilled maybe 8 to 10 feet per hour with a roller cone bit. When we went to the inclined well, we pushed that to and 40 hours on bottom. When we went to PDC bits on the inclined well, we pushed that to 60 or 80 feet per hour and drilling lengths of maybe 700 feet. As we move further, and we had very, very good interactions with PDC bid companies, and I will tip my hat to NOV, very, very good interactions with them. And on the last well, we were drilling 100 feet per hour and on bottom for 2,000 feet. This is groundbreaking. I just cannot see going back. We will not go back at Forge. I advocate people giving them a chance. Now, there's more to it than just the bit. We really imposed on the geothermal industry in the United States the concepts of what Fred Dupree's called and Sam Neunert called physics-based drilling. And this is a strong application of mechanical specific energy and using feedback from the bit to look for dysfunction. And once you identify a dysfunction, is find out what's causing that dysfunction, what's limiting the rate of penetration, and resolving that. And that's why we had a very good relationship with the bit vendor, is that they were making changes on the fly, as well as the directional companies.
Okay, and I think now we're going to the very last question. It's also a very long one, but let's try here. So the question here, you mentioned that drilling-related rugosity was fairly high. It could become a concern for the long-term well and monitoring system life and the integrity. If this is the case, have changes been considered to the drilling approach or technology? Here's an example of rotary steerable systems or to the completion design, hole under ream to casing diameters, etc.
Yeah. I mean, this first of all, we're only speculating that it's going to be an issue. But I mean, you look at this and just from a practical point of view, you say, hey, these ledges could be a problem running casing. I mean, we have enough trouble with cementing as it is. You can have pinch points, and particularly with moving towards hydraulic fracturing in this industry, looking at experience in the oil patch of failed casing, there can be a concern. And so, as the questioner points out, we do want to move towards this, and rotary steerable certainly is one potential solution. We will try rotary steerable. We have tried rotary steerable. The drawback with rotary steerable that we've had in the past, we've tried conventional rotary steerable and just mechanical rotary steerable. And the mechanical rotary steerable, we had trouble transferring weight to the bit. And the key for success for the PDCs, and I need to repeat this, is you need to be able to put weight on the bit, and you need to be able to put weight on the bit approaching the limit, the manufacturer's limit. And of course, you'll run tests to determine what the optimum weight on bit is and RPMs. But the rugosity is something we want to deal with. As to the potential for reaming, we reamed this. The pictures you saw were after a significant degree of reaming with multiple runs with various different reaming technologies, roller reamers, string reamers, and a lot of bit runs to try and avoid that and to get cuttings out of the hole. So I think one of the observations is that, you know, granite is a less forgiving rock than some of the sedimentary rocks that our colleagues in oil and gas are accustomed to, where reaming and just different bit runs can be eliminating some of these ledges and rough spots. These were preserved, and so I think that as the questioner pointed out, the key to solving this is when you initially drill the hole, not when you try and remediate it.
There are still tons of questions here. Unfortunately, we're not able to answer them. But with that, John, I would like to thank you kindly for a fantastic presentation and the willingness to be grilled by all these questions. Thank you so much for being with us today. Thank you to the audience for your engagement and participating. With that, I wish you a fantastic weekend. Thank you, John, to your team at Utah for the great work that you do and for sharing all these details with us. Thank you so much.
Thank you.